Hello, everybody. Hope you are having a great week. So, this is my lecture for week 13, session 2. And let's continue chapter 5. And today we are going to discuss the pipe networks. In previous lectures, you learned about, the single pipes, series pipe, parallel pipes, and now we discuss the pipe networks. So normally pipe networks are include, series pipes and parallel pipes. So we have, both these two actually cases in, uh, you know, uh, pipe networks. So in most cases, we may have, actually, different pipes, with different lengths, different diameters. So they will have, different friction factor. We may have, some, inlets, some exits. We may have different, several, loops for the, fluid. So as an example, for the pipe network, we can just, for example, discuss the pipe network in, for example, houses, in, let's say, a factory, in, a city. So, you can use actually this, method to analyze the pipe networks, for different, cases. So the main objectives of, this actually pipe network problem is to determine the, volumetric flow rate in, different pipes. So we normally have, information for the pipes, lengths, for the pipe, diameters, so the relative roughness, and then what you need to do, you need to find the volumetric flow rate in each pipe. So as a first step to analyze the pipe networks, what you need to do, you need to just label all, pipes. So you can use numbers to label, all pipes. So here you have more than one pipe. You need to label, pipes. So you can start from one point and then you can label all, pipes. Moreover, you need to label all, junctions, correct? So for example, here, we have several junctions. So normally we use letter to, label the junctions. So you can just, use a letter to label, different junction. And then moreover, guys, in some cases you can simplify, the loops. For example, here for, junction E1 and E2, they are so close. So you can assume that E1 exactly is on the, E2. So we have actual pipe 2 goes, through E2, and then, fluid flows, to pipe 10 and 7. And so what we do, we normally need to write the Bernoulli equation and continuity equation to solve the, pipe networks. So here, I will go over a step-by-step method to analyze pipe networks. Again, the main actually, topic of this, pipe network is to find, the volumetric flow rate of each pipe. So what you need to do, you need to write the start from the continuity equation. You can write the continuity equation for the actually whole system. If you consider this, before that, sorry, before you just write the continuity equation, you need to assume a flow direction for each, actually fluid flow, in each pipe. This is totally, arbitrary. So you can select, randomly, direction for, all, fluids, in the fluids flow, in the pipes. So select a flow direction. Uh, or you can totally select, randomly, direction. Or what you can do, you can start from one point and then, you can select a direction. For example, here is the inlet. So this is the inlet. You can assume that fluids flow, in this direction in pipe 4, and then from the left to the right, to pipe 3. And then here, this is the exit. So then you can assume that, fluid from, pipe actually 4 goes through this junction B, and then, goes from left to right in the pipe 1. And then you can just select a direction for all other, fluids flow. this is the first step. Then what you can do, you can write the overall continuity equation, the continuity equation for the whole system. Here we are normally dealing with the incompressible fluids. So you can write the volumetric, actually, continuity equation for volumetric flow rate. So you can write the sigma volumetric flow rate in equals to sigma volumetric flow rate out. For this example, there is one inlet here, and the other one here. So there are three inlets. You can write QA, keep in your mind that the Q is volumetric flow rate. QA plus QF plus QG equals the QB plus QD plus QH. This is, the overall continuity equation. And then you can write the continuity equation for each junction. If we have n junction, you can set n, continuity equation for these junctions, correct? For example, the continuity equation for junction B is Q4 equals to QB plus Q1. Or the continuity equation for junction C is Q1 plus Q2 equals to Q5, correct? So you can just set the continuity equation for, if you have n junction, you can write n equation. But keep in your mind that n minus 1 equation are independent from this n equation. So you can set n equation, but n minus 1 equations are independent. Then keep in your mind that totally, we have n independent equation. Why n independent equation? Because you have n minus 1 independent equation for the junctions, and then you have one independent equation for the overall, mass balance or volumetric flow rate. So then the total will be n. Now, this is, for the continuity equation. Now, what you need to do, you need to just write the Bernoulli equation, or you need to write the delta P equation. Before that, you need to identify the loops. Here, there are three loops. And then you need to select a direction, for the loops. Here, I assume that, all loops are, clockwise. So, three loops, and then you need to select a direction, for the, loop as positive. Then, if we have n loops, you can set, m, equation for these, loops. M delta P, equation. You can write the delta P for this loop, delta P for this loop, and the delta P for this loop. Keep in your mind that the delta P is 0 for the loop. If you start from this point and then write, the delta P equation for this loop, the delta P will be 0. And then we will use the Bernoulli equation to simplify the pressure drop equations. How? For instance, guys, for loop 1, we can write the delta P BC plus delta P CE plus delta P EA plus delta P AB equals to 0. Correct? And then what you can do, you can find equation for delta P for each delta P in this equation from the Bernoulli equation. For example, if you set the Bernoulli equation for point B between B and C, we can just write the Bernoulli equation, correct? So pressure, volume, elevation, and then the head losses. So for point B to C, you can cancel the velocities. Velocity B equals to the velocity C, because the pipe size is constant, the diameter is constant, so you can cancel the velocities. You can cancel the Z elevation. Then if we assume that the minor losses are negligible, then you can find the PB or the delta P between BC, correct? We are looking for the PB, delta P BC, or PB minus PC. This is the equation for the delta P from the Bernoulli equation for the BC. So if we have a circular pipe, we can find a correlation for velocity from the definition for volumetric flow rate. So we can write the volumetric flow rate Q1 equals to the A1 times V1, and then from here you can find the V1. V1 is Q1 over A1, and A1 is pi D1 squared over 4. If you substitute for velocity from this equation into this delta P equation, we can write the delta P BC equals to C1 F1 Q1 squared. What is the C1? C1 is a constant. It's 8 rho L pi squared D15. Keep in your mind that you have all this information. You have the length, you have the diameter, you have the density, so you can find the C1. So in this equation, actually, both friction factor and Q are unknown. Now, what you can do, you can find the delta P CE, EA, and AB from the Bernoulli equation for actually, and then you can substitute into this equation. So um, now, you can repeat, actually this procedure to find, the delta P for other, parts. I mean, this one, and, by 4. Now, uh, please pause this video, spend 5 minutes, and then try to find the, delta PCE, delta PEA, and delta PAE. And then what's the conclusion based on, your, results? Okay, so, for example, if you want to write, the Bernoulli equation between point E and C, look guys, we are looking for the delta PCE, but you need to write the Bernoulli equation between point E and C. Why? Because the flow direction is from point E to C, correct? Look guys, so again, you're looking for the delta PCE, but you need to write the Bernoulli equation between point E and C. Why? Because the flow direction is from point E to point C, correct? So if you set this equation, you can write PE over rho G plus Z E plus V squared over 2G plus head losses. Sorry, minus head losses equals to the pressure at this point, kinetic energy, and Z, correct? So then again, you can cancel the velocities. Velocities are the same. You can cancel the Z. There is no pump. There is no turbine. And then here you can see that the delta PCE equals to the negative HL, correct? So, and you saw that why, we have this negative, because you wrote the, Bernoulli equation for point E to C. Now, this is the, actual equation for the delta PC. Again, if you substitute for the velocity from the, equation for volumetric flow rate into this equation, we can write the delta PCE equals to the negative C2 F2 Q2 square. So again, C is a constant value, friction factor and volumetric flow rate are unknown. What's the conclusion, guys? If you compare, actually these two terms that we developed for delta P, for these two pipes, you can see that when the fluid flow and loop direction and loops are in the same direction, you can write the delta P equals to the plus CI FI QI squared. When the fluid flow and the loop are in the opposite direction, you should write the delta P equals the negative CI FI QI squared. So you can actually develop a general equation based on this conclusion. You can write the delta P for each loop equals to the CI plus minus CI FI QI squared, correct? And then CI is a constant value. It depends on the lengths and diameters. And so you can simply, you don't need to actually write the Bernoulli equation, for each part. You can simply use this equation to find, the delta P for each, actually, part. Now, please pause this video and then spend, 2 minutes to just rewrite, this equation based on, this equation for the delta P. Okay, look guys, if you just use this equation, you can write the delta PBC equals to the C1 F1 Q1 squared, correct? Minus, why minus? Because they are in the opposite direction. Minus C2 F2 Q2 squared. And then again, minus Why minus? Because this is the loop direction and this is the fluid flow direction, correct? Minus C3 F3 Q3 squared, and then for the fourth one, loop and fluid flow are in the same direction, plus C4 F4 Q4 squared. If you substitute for these values into this equation, you can actually develop an equation for the loop, correct? So for the loop one, you can set this equation. Keep in your mind that in this equation, friction factors and Q's are unknown. Now, what you need to do, you need to actually write the equation based on, the Bernoulli equation and delta P for loop 2 and loop 3 as well. So, yeah, here you can see, the delta, the, equation based on, for the loop 2 and loop 3 based on, that general equation. Again, you don't need to write the, Bernoulli equation. You don't need to set the Bernoulli equation for each part. You can simply use, the delta P equals this plus minus Ci Fi Qi squared. Now, you can set M equation. Here we have three loops, so you just set three equations for, based on the Bernoulli equation and delta P. Now, what you need to do, you have M equation for the loops and N minus 1 equation from the continuity equation. You need to solve all these equations simultaneously to find, the friction factors, to find the unknown parameters, to find, the friction factors and Q's. So the question is that how we can solve this equation. To solve this equation, you can use one of these two methods. The first method is the conventional method. So what is the conventional method? The conventional method is based on, the iteration method. So you need to assume a value for the friction factors, and then you should actually substitute this friction factor in the, equations for, from the Bernoulli equation and also equation from the continuity equation to find, all volumetric flow rates. Now you have the volumetric flow rates, you have the diameters, you can find the velocities, you have the velocities, you can find the Reynolds number, you have the Reynolds number, and then you can find the new, friction factors. If you have a laminar flow or, a turbulent. If you have a turbulent flow, use the Chen equation. This is the Chen equation. If it's a laminar flow, you can use this equation to find the friction factor. And then you need to compare, the friction factor news with the actually first guess or with the previous guess. If they are pretty close, if the difference is less than 0.003, you are good for all, friction factors. Otherwise, you need to repeat, the procedure with the new, values. Here, is the flow chart, how this method, works. So, for example, for this, loop, you have, for this example, you have three equations for the loops, and you have n minus 1 equation. So you need to assume, 10 friction factors, and then you need to solve this process. This is not, actually a straightforward method to solve, this equation. Why? Because these two equations, correct, they are actually, we have the second order. They are non-linear, equations. These, Q's. So they are non-linear, and then it's really, it's not that much easy, to just use to solve this, problem by using, this method, the friction factors, and then solve it. So the second method is the Hardy-Cross method. What is the Hardy-Cross method? In Hardy-Cross method, again, we use the iteration method. However, in this method, we try to actually assume, we try to start from the Q's. We can assume 2, 3 Q's, and then by using the continuity equation, you can find all other Q's, correct? Now you have all other Q's, you can find, a delta Q correction factor, and then what's this correction factor, we will discuss it. And then you can find the new Q. And then based on the new Q, you can make a decision if your assumption is good or you need to repeat the process. Now, Here you can see, the actual flow chart for the second method. So we start from some flow rates, 2, 3 flow rates. In most cases, for this course, 2 flow rates is enough. So you need to start from the 2 flow rates, and then you can find, the other flow rates by using the continuity equation. Now you have all, Q's. You can find the velocities. Keep in your mind that, guys, Q can be positive or negative. If your Q is negative, guys, don't worry. Because it depends to the direction that you select, correct? So if it's negative, guys, don't worry, eventually, you can fix it. But keep in your mind that Q can be positive or negative, but velocity is always, positive. So you need to use the absolute value to calculate Q. So you have the velocity, you can find the Reynolds number, you have the Reynolds number, you can find the friction factor, and then you can find the delta Pi. How you can find the delta Pi from, the Bernoulli equation, or you can write the delta Pi equals to the Ci Fi Qi squared, correct? So the delta Pi equals to Ci Fi plus minus Ci Fi Qi squared. Now, you have the delta Pi. You can actually calculate the delta Pi over Qi. This term is always positive. Why? Because the delta P and Qi, and they have the same, uh, uh, you know, uh, sign. So I mean, delta P. If the Q is negative, delta P will be negative. If Q is positive, delta P is positive. So keep in your mind that always this term is positive, but Q and delta P can be either negative or positive. And then you can calculate the delta Q. What is the delta Q? The delta Q is sigma delta Pi over 2 sigma delta Pi over Qi. And then you can calculate the second Q. If the difference between second Q and this first Q, or if the difference is less than 2%, if the error is less than 2%, you are good. Otherwise, you need to repeat this procedure. What is the advantage of this method? If you want to compare this method with the conventional method, the advantage is that in this process you start with 2 or 3 assumptions. Keep in your mind that in the conventional method, you need to assume n friction factor. For example, for the previous example, you need to start with 10 values, 10 assumption, 10 friction factor. However, here you start from 2 or 3 Q, and then this is actually more straightforward to solve the problems. Now, so let's just go over, all these, methods, all these, steps for this, example. We have 2 loops, we have, 7 pipes, and then, some junctions. So what you need to do as a first step, you need to just label all junctions and pipe. So we already, label all junctions and pipe. Then what you need to do, you need to assume a flow direction in each pipe. For example, you can start from, this one. This is inlet. This is normally given. The inlet and exits are normally given. So this is the inlet. You have the inlet. So this is the inlet. You can assume that this flow actually is divided into, pipe 4 and pipe 1. Then this is pipe 1 here at junction B. You can assume that it's divided into, pipe two section for pipe 5 and pipe 2. So you can select a direction for all pipes. Then we have 2 loops. You need to select 2 actually direction. Normally you can use the clockwise direction. So you actually label all pipes, you label all junctions, and then you select a flow direction and a loop direction. So what you need to do, you need to write the overall mass balance or overall volumetric flow rate balance. So for this actually system, we have just one inlet and there are 1, 2, 3, 4 exits. So you can write Q in equals to this one plus this one plus this one. So this actually 4 values. So look, guys, what's the advantage of this actually overall continuity equation? In some cases, one of these exits or inlets are unknown, and if you write the continuity equation, the overall continuity equation, you can find that unknown parameter. Moreover, you need to check it. You need to make sure that the continuity equation is valid. So here the right side, the Q in equals the Q out, so the continuity equation is valid. So the next step, you need to write the continuity equation for each junction. So here there are 6 junctions, so you can write, continuity equation for each junction. For example, for junction A, we can write point 125 equals to Q1 plus Q4. Or for example, for junction, let's say C, you can write Q5 equals to 0.012 plus Q6, correct? Just write, all continuity equations. So we have 6 equations. Keep in your mind that 5 equations of these equations are independent, n minus 1. Now let's look at, this continuity equation, guys. If you look at this continuity equation, you can see that if you have two, volumetric flow rates, you can calculate all other volumetric flow rates. For example, if you have Q1 and Q2, if you have Q1 and Q2, you can find Q5, correct, from this equation. You have the Q1, and then you can find Q4 from equation A, correct? You already found Q5 from equation B, so you can find Q6 from this equation. If you check it, guys, you can see that by having the Q1 and Q2, you are able to calculate all other volumetric flow rates. So we will discuss it, later. Now, what's the next step? So you need to identify each loop. You already identify each loop, and then the direction, and then you need to write the pressure drop equation for each loop. For example, for loop 1, you can write delta PAB plus BE plus CE plus DA equals to 0. Or you can write plus C1 F1 Q1 squared plus C2 F2 Q2 squared minus Q3 F3, sorry, minus C3 F3 Q3 squared minus C4 F4 Q4 squared equals to 0, correct? And then you can write, this actually, the same equation for the loop 2. Now, you just wrote the pressure drop equation, then you can simplify, the continuity equation that you already wrote in the previous, slide. So if you just actually rewrite, those continuity equation, you can see that by having the Q1 and Q2, you can find, all other, Qs. We already discussed it, in the previous slide. Now, so this is a, actually available information. We have 7 pipes. We have the diameters. Lengths are known. These are normally given. So you can find the C. This is the definition for the C. And then, the relative roughness. So these are all available information. Normally you have this part, and then you need to calculate C, and then you need to find, epsilon, and then calculate epsilon over the relative roughness. Now, what you need to do, you need to start, from the Q1 and Q2. You need to assume a value, initial value for Q1 and Q2. Here, I assume that the Q1 is 0.06 cubic meter per second and Q2 is 0.02 cubic meter per second. You can start from any value, guys. It's totally up to you. Eventually, you can get, the results. However, if you start, from a reasonable value, you will get, the results. You need to less, iteration, iteration to find the final, answers. Here, I started from 0.06 for Q1. Why? Look, guys, the inlet volumetric flow rate is known. It's 0.125, cubic meter per second. Then based on the diameter for pipe 1 and 4, you can make a decision, for, a reasonable, volumetric flow rate in pipe 1. Look, if this direction is correct, we have no idea if this direction is correct, but if this direction is correct, based on this diameter, probably 50% of the, flow goes through pipe 1. correct? This is not actually, guys, exact value. Why? Because it depends to the length, it depends, to the epsilon over the, it depends, to several, factors. But that's a good assumption as a starting point. So I assume that, 50% of this volumetric fluid goes through, pipe 1. They have the same, diameter. So I selected Q1 equals to 0.06. And then again here, they have the same, diameters, correct? And then you can assume that the 50% goes through pipe 2 and 50% goes through pipe 5, or I started from 0.02, correct? So this is, the initial values, and I started, from these values. You have the Q1, Q2. Now you can use the continuity equation to find Q3 through Q7. Right? You have, this correlation. By this assumption, you can find the, Q1, Q3 through Q7. So let's go to the next slide. Okay, look, guys. So here is, Q1 and Q2, correct? We assume, these two values, and then you found Q3 and Q4, Q5 and Q6. Keep in your mind that, guys, and also Q7. Keep in your mind that the first thing is that, look, some Q's are negative. Don't worry. That's fine, correct? Q can be either negative or positive. That's totally fine. But keep in your mind that the sign for Q and delta P are the same, correct? So this is negative, this is negative. We'll discuss it. This is the first thing. Some Q's are negative. That's fine. The other thing is that, guys, pipe 2 is common between loop 1 and loop 2. Yeah, here, look. Pipe 2 is common, between, pipe loop 1 and loop 2. So you need to write it for both two loops, correct? So this is the information for loop 1, and this is the information for loop 2. And then if you look at, this table, you can see that, pipe 2 is available in both two, loops. However, for the second loop, the, value for the Q is negative. Why it's negative? Because the fluid flow and, loops for the second loop are, in the opposite direction, correct? So I assume that I started with 0.02 for the, Q2 based on, this assumption from the loop 1. So for the second loop, this value will be negative. So Q2 for the second loop is the negative value. Then you can find the velocities. You have all, Q's. Keep in your mind that the velocity is actually positive value. You need to use the absolute value. Then you can find the Reynolds number. By having the Reynolds number, you can find the friction factors. Now you have the friction factor. You can find the delta P for each pipe. What's the equation for the delta P? You can write the delta P I equals the C plus minus CI FI QI squared, correct? And then you can find the delta P. Again, the delta P, the sign for the delta P and Q are the same. Now you have the delta P. You can calculate the sigma delta P. This is the sigma delta P, correct? For both these two loops. The next step, you need to find the delta Pi over Q. So you have the delta P, you just need to find the delta Pi over Q. Keep in your mind that delta Pi over Q is always positive. Now, you have all delta Pi over Q, you can find the sigma delta Pi over Q, correct? And then you can find the delta Q for each loop. This is the delta Pi, this term, over actually negative sigma delta Pi, negative sigma delta Pi, over 2 times sigma delta Pi over Qi, which is, this term. So you can find the delta Q. Now you have the delta Q. You can calculate the Q new for each pipe. How? The second, value for the Q is the first values plus delta Q. So you can find the new Q for all pipes, but keep in your mind that for the pipe 2, because pipe 2 is common between, both actually these two, loops, you need to apply both delta Qs for pipe 1 and pipe 2 to find the second Q for pipe 2. Correct? Look, this is the initial value, and then you need to apply both these two, delta Q for loop 1 and delta Q for loop 2. And then keep in your mind that the delta Q for the loop 2 must be negative. Why? Because the fluid flow in pipe 2 and loop direction are in opposite direction. Now you can find the Q. This is the second iteration values, correct? Again, look, the value for Q in loop 2 is in the opposite, sign of Q in the first, loop. So again, you can repeat this process. You can find the Reynolds number, friction factors, delta P's, and then you can find the delta Q new, and then you can find the Q new. So what you need to do, you need to calculate, the percentage error. If the percentage error between two, sequence Q is less than 2%, you are good. Otherwise, you need to repeat this procedure. Keep in your mind that this actually error must be less than 2% for all pipes. If you have two pipes with this, for example, that satisfy this, requirement, and then you have two pipes that, they don't, satisfy this criteria, you need to repeat this, procedure, this iteration, and then when all pipes satisfy, this, 2% error, you are good, and then you can stop the iteration, procedure. So after all calculation, this is the values for the Q. Keep in your mind that what you need to do, you need to actually report all Q's in positive, actually values, positive values. However, the negative value means that the direction that you select for part 3 is wrong. You need to just select an opposite direction for fluid flow in pipe 3 and also in pipe 4 and pipe 7. Correct? For these three pipes, pipe 3, pipe 4, and pipe 7, you need to just change the flow direction. And then these are all Q's. So as a summary, what you need to do, you need to start to assume, actually, you need to label all junctions, all pipes, you need to identify the loops, select a direction for the loops, and then you need to check the continuity equation for the entire network. You need to write n minus 1 continuity equation or n continuity equation, and then keep in your mind that n minus 1 continuity equation are independent for n junction. And then what you need to do, you need to actually write, you need to assume 2 or 3, volumetric flow rate, and then from the continuity equations, you can find other, Q's. Now you have all other Q's. You can find the Reynolds numbers, you can find the friction factors, and then you can find, the delta P, and then from the sigma delta P, and then you can find the delta Pi over Q, and then you can find the sigma delta Pi, sigma delta Pi over Qi, and then you can find the delta Q, and from the delta Q, you can calculate the second Q, and then you can compare, Q with the previous, assumption. So this is my lecture for today, guys. I will solve one problem next lecture. So I will share, Excel file, and then we work, together to solve a problem from this, section. Thank you so much, and have a great day.